Welcome back to the channel. This is Castra. If this is your first time here, I'm a machine tool designer and manufacturer by trade, and at the moment I'm working on a DIY super precision 5-axis milling and turning machine, and I'm building that in my own garage. There are other videos on the channel explaining the process from design to some of the assemblies, or some live videos on the live section of the channel. So if you're into this stuff, I recommend to please check those out as well. Apologies for being not being around for a while. I've been quite busy and a lot of traveling, but I managed to spend a few more days on the build and assembled a few other things with the help of one of my friends over a long weekend. So I will in a moment to strap the camera onto myself and give you an update of what's been added to the machine recently. There's also a lot of questions, and I really welcome the questions. There's a lot of things that people ask. I might end up doing a Q&A session, maybe a live session. Please let me know in the comments if you would like to attend a live Q&A session that we can talk about anything that you might need to ask me regarding the project. And I've got some other friends who know me personally and my background, and they've been telling me that maybe it's a good idea to show some of the other designs that I've got. I've got more than, I don't know, maybe 30, 40 different types of CNC machine tools that I've designed over the years, and all of them have been manufactured. Some of them, a lot of those machines have been manufactured, and so there's a lot that I can share and maybe expand the channel a bit as well. So let me know if you would like to see other types of CNC machine tools as well. So maybe we can do something about that. I just found a place on YouTube Analytics, and it says that, I don't know, maybe 80% of the people who are watching the videos are not subscribed. So please consider subscribing to the channel, because I hear that it can improve with the algorithm, and it can reach to more people. So if you like what you see, please consider subscribing to the channel. Okay, with that said, I'll get the camera and we'll have a look at the machine and see what's been going on recently. Okay, as you can see, we now have some motors installed. So where should we start? I think we can start with the spindle. Okay, so this is a Chinese-built spindle. It was recommended to me by one of my friends who's a machine tool manufacturer. They've been using this spindle on their products in Europe for many, many years. They quite like them. It's pretty accurate in terms of runout. The spec of this spindle, as you can see, it's a pretty compact design. It's 62 millimeters in diameter in this sort of the nose section. It's automatic tool changing, and the tool taper is called T11, which is very similar to the ISO10s, so very, very small tool holders. It's water cooled, so there is a water inlet and a water outlet. This particular model, as per my request, has been fitted with an encoder, so it allows me to do rigid tapping as well on very small taps, obviously M2, M3 maybe maximum. It's 1.8 kilowatts, 60,000 RPM, and the run out is better than a micron. I tested with my DTI, but it didn't have any run out. Obviously, I only checked the nose. I've ordered a test bar at some point. I will check the run out over a length as well. Yeah, it's got a few sensors as well, such as the tool presence sensor, and if the pressure drops. There's a few air inlets to cool down the bearings, and also push away any coolant or debris that might try to get near the bearing. So it's pressurized. It's a pressurized chamber, if you like. So it's a pretty cool spindle. I will have a tool changer. If you've watched the design video, the tool changer disc will be here. It's got 28 pockets, and it's mounted on a swing arm that will swing inside, and the spindle can change the tools, and that's got its own rotating axis as well. So that's the spindle. It's mounted on this bracket. This bracket has got two pieces. This is the first piece that you can see. There's another piece behind it, and these two pieces, they have a curvature, and they've been lapped together, so they've got perfect contact, and the rear face is being lapped as well. So that allows me to basically, with all of these grub screws that you can see are all the way around, so there's like 2, 4, 6, 8 grub screws that can manipulate and move this this spindle, so that I can make some adjustments to basically make the spindle line perpendicular and parallel to the relevant axes. So for example, if by any chance some of these parts, they've got some small errors, say for example this linear block's got a 2 micron taper. So if it's got a 2 micron taper, obviously this axis will be sitting at an angle, and there's a stack of tolerances all the way from there up to where the spindle is. So by having these adjustability, I can in theory get away from any sort of errors that might be in this area. So that curvature is to take out any errors in this direction, but there's also a gap in around it, so I can get away or remove any misalignments in this direction as well. So by combining those two, I should be able to clock up the test bar and bring the spindle completely vertical. And then obviously these grub screws are just to pivoting and moving this around, and they've got a secondary lock knot to just hold them in place, but the actual thing that holds the spindle in place are not the grub screws, but actually are these 4 M8 bolts, which are quite strong, and they go all the way through the granite, and on the other side there's a nut, and they've got these washers that are locking washers that I just love them. I might show you at some other point why I really like these washers. So with these, then obviously we can align the spindle, and if by any chance we needed a little bit more clearance in the Z-axis, I can just loosen this bolt up, and then the spindle can slide up and down, and then I can just hold it again in place. So that can give me a little bit more sort of Z clearance if I need it. Then up here I've got the Z-axis servo motor with its own bracket, and there's also a coupling that you can see from here. So there's a coupling. It's a bellows type coupling. These are, I would say at the moment, these are the most accurate ones that you can find. So there's absolutely zero backlash, but because it's kind of made from one piece, it's not one piece. There's 2 aluminium pieces, and then there's the metal sort of, I think it's a stainless steel bellows in between them. But the way that they're joined together, it kind of makes them as one piece. So it's better than those disc couplings, and far better than those plasticky couplings. It doesn't allow for a lot of misalignment between the 2 shafts, but I made a tool, a little tool, like one of these couplings, but it was just a rigid piece. That I got it ground from both directions, one the size of the diameter of the ball screw, the other for the servo motor, and I basically put that in place first and brought these two to the center line of each other, so the servo to the center line of the bolt screw, and then I remove that, and then I put the coupling back in place, and with that way I could bring these two to a very good centricity, if that's a word. So they are in the exact center point of each other, because there's no way that you can put a DTI or something in this very confined space. So I used that little tool that I made for this purpose. It must be somewhere around here. This is a Beckhoff servo motor. This has an absolute encoder. I can't remember what was the exact spec of the encoder, but I think it's 24 bits, but I'm not really sure. It's single turn absolute encoder. I didn't need a multi-turn because I've got linear scale on all three linear axes. And this one has a zero backlash, what you call it, a brake as well, so for the z-axis not to drop down. I think on the previous video I showed you all the things that are going on around here. So these are for the cooling of the ball screw nut. We ended up putting these stainless steel springs inside the tubes, so when you bend them a lot, they don't make a kink. I learned this word from some of you last time, so thanks for that. That's for the grease inlet of that bolt screw. Then these two are for the linear blocks, and these will be fed through hoses, so a grease tube like this, which is a high pressure, I think it's 30 MPa working pressure and a bursting pressure of 90 MPa. So that's for the grease. Anything else around here? No, I think that's it. I fixed these plates with epoxy resin. So there was a hole. I don't know if you can see it. There's a hole here, and then once this was in position, then I drilled into the granite, and then I filled it up with epoxy resin, and that's how I pinned these two pieces together. I originally wanted to use an expanding pin, which is something that I've used on various other machines, but I realized that by hammering it down I can actually slightly move these plates, so I dropped that idea. What else? Most of our time, to be honest, was spent on this mess, which is, I think you can see it now. So this is a progressive grease distribution system. It's got loads of copper pipes, and these are for these hoses that will be eventually connected to them. These are clever little devices. These are essentially kind of a mechanical pump. There's a lot of small ball bearings inside and a lot of channels. So there is an inlet up top, as you can see there. So that's the grease inlet. So that will be connected to my grease pump. It's an automatic grease pump. Then the grease will go inside, and each time you pump a little bit, those ball bearings move slightly, and it will push out a certain amount of grease out of one of these. So if you've got, for example, 14 tubes, which is in my case, you need to start and stop it 14 times, and each time you push some grease out, only that amount will go to one of these outlets. So it's a very effective way of evenly greasing all the connections. Because there's a difference in length of these tubes, before I actually installed them, I pre-filled them with the grease that I intend to put into the pump. There is there was a lot of work around here, because the clearance between these, and there are some other plates that I have not installed yet, are really, really tight. Very small clearances around here. Then we've got a similar setup for the X-axis servo motor. I'm not sure if I want to call this Y or X still, but there's one here. Same thing with the coupling. Same scenario for the Y-axis. Again, this bracket is aluminium. This is stainless steel. This has been pinned with the same method that I showed you. Also, the BK and the BF, or rather I think it's an EK and EF, these bearings, they've been pinned with the same method as well. So using epoxy resin or a type of epoxy glue. So yeah, these have been installed as well, firmly held in place. I don't think there's much else to say apart from these. I think you've seen these at some point. So these are covers, way covers. They will go around two shafts, and then they will get connected to this side and the other way from that side, so that nothing will get into this area. And we're going to have a plate up here and a plate back there. We spent recently a lot of time working on the sheet metal. It's been a lot of work, to be honest. It's been a nightmare, but yeah. I think that's about it. I'm gonna pause the video now, but I'll show you a little view of the control cabinet as well, because we ended up working on that one too. Yeah, if you've got any questions from the mechanical parts, please leave some comments down below, and I hope to be able to answer them. One thing that I should add is we decided, based on some of the comments that people made, we decided to add a brake for the fourth axis as well. So if I do an update video on the design, you will see that part too. It was something that we could have added relatively simple, so we've done that as well. Okay, so I'll show you a little quick overview of the control cabinet, and yeah. Okay, so this is the control cabinet. As you can see, we've got some wiring going on now. So we've connected some of these wires to the drives. So that's the A-axis drive, that's the C-axis drive. These are the Beckhoff twin drives. So each of these can control two motors. One is for the X and the Y, the other one is for the Z and the spindle. The spindle will be controlled by one of these as well. And they've got a second encoder input too. So one for each axis, and that's the first one is the power supply module and the EtherCAT module. Then we've got two power switching units. Then that's the brains of the system. We have started to wire some of these EtherCAT IOs. There are a load of relays over there. There's more relays down there. Some fuses going on. It's pretty tight, it's pretty compact, as you can see. We've got one fan up here and one sort of filter inlet down there. This is not going to be an IP enclosed control cabinet, because this whole machine will go inside a temperature controlled enclosure or a chamber, and there's going to be right here next to it, next to the control cabinet, a big AC unit to regulate the whole temperature. So I wasn't really bothered about cutting an opening there, or there's another opening there, but you can't see it obviously because it's been covered with this cardboard piece to prevent anything falling down. But that's where the cables will go up. And that's where the cables and some of the hoses will come into the control cabinet. But yeah, I wasn't really bothered about keeping the IP rating of the control cabinet because it's going to be an enclosed area. But yeah, that's about it really. Over time, we'll add more stuff to this.
And if you've got any questions about the electrical parts, please comment them below as well. And yeah, once again, consider subscribing to the channel, and I hope to catch you in the next one. Cheers.